Sorry, excuse me, my video just stopped. So as we were discussing, okay, okay, so as we were discussing, for a base area of 10 meter square, Cu equals 13.9 into 10 to power 4 into square root 1.125 over 10. This comes out to be, let me write in red. So this comes out to be 4.66 into 10 to power 4 kilonewton per meter cube. And then from this Cu we can calculate C tau, which is equal to half of Cu, and this will come out to be 2.33 into 10 to power 4 kilonewton per meter cube. And similarly we can calculate C5, which is equal to 1.73 times Cu, and this will come out to be 1.73 into 4.66 10 to power 4 will come out to be 8.06 into 10 to power 4 kilonewton per meter cube. Okay, so this was the second part of the problem. Let's move on to the third part. Okay, now if we look at the graph, at our peak frequency, our natural frequency, we have an amplitude of 0.14 mm. So we can say that resonant amplitude of vibration at a frequency of 43 Hertz Now we know that our natural frequency equals our angular frequency equals 2 pi times natural frequency. So we will have 86 pi radians per second, and our weight, which is mg, is 22 kilonewton. So from spring constant. For the soil stiffness, we can calculate the spring constant as m omega n square. This will be 22 over 9.8 into 86 pi square multiplied by 10 to the power minus 3 for our unit of the system of units. So the answer for K is, we get a stiffness of 163.9 kilonewton per mm. Okay, moving forward, the amplitude of vibration at resonance is given by we can write A Z is equal to dynamic force over spring constant by 2 times the damping factor, or we can write it as P naught by 2k eta. So we know the value of K. We know the value of amplitude at resonance. We have to calculate P naught. At resonance frequency, we can calculate as 5 times 43 by 50 square. This comes out to be 3.7 kilonewton. So we will have a damping factor of P naught over twice A times K. This is 3.7 over 2 into 163.9 into 0.14. So our final damping factor value will be, let me calculate, this comes out to be 0.08. So that is the answer to the final part. We have some time for one more problem, so let's try to do that. Okay, so the successive peaks from a free vibration record obtained from initial displacement or sudden release test on a block resting on soil are tabulated below. Okay, compute the natural frequency of vibration of the block, and also the damping in the foundation. Okay, so let me insert a table. Mm, 1, 2, 3, 4, 5, 6, 7, 8. Okay, we have time here in seconds, then we have peak amplitude in mm. Let's tabulate this. 0, 0, 0.02, 0.04, 6, 0.08, 0.1. Okay, this is 0.14, 0.16, 0.18, 0.2, 0.3, 0.4, 6, 8. Okay. Two more. 0.26 and 0.28. Let me give you the values. Excuse me. 16 minus 12, 8 minus 6, 4 minus 3, 2 minus 1.5, 1 minus 0.75, 0.5 minus 0.38, 0.25 minus 0.19, 0.13 minus 0.1. Where's the mistake? 4, 6, 8, 2. Is there a... Let me check again. Okay, there is one more row here. That's 0.3, and 0.10 is at 0.3. Okay, Okay, so these are the values given to us. Now the question is asking us to calculate the frequency of vibration of the block and the damping also. So first, excuse me. Okay, we can see that the interval between the positive or the negative peaks, like we can say, if it is like this, we have a positive peak and a negative peak. So this interval between two positive or two negative peaks, we can see here is 0 0.04, 0 0.04, 0 0.04 and so on. So we can say that the interval between two crests or troughs is 0.04 second. So this is the time period of vibration of block. Natural frequency is equivalent to 1 by t equals 1 by 0 0.04. This is equivalent to 25 hertz. Amplitude ratio between successive peaks of same sign that is x1 by x2 equals, we can say here, 16 by 8, 8 by 4, 4 by 2, 2 by 1 and so on, which is 2.